like to welcome back Dr. Ben Goertzel. Ben is going to tell us about the AI agent simulation of the COVID-19 pandemic that we've been running for a few weeks now, and that it was at the center of the COVID-19 simulation summit that we held now a few months back now, and finally we have some amazing results to talk about. So over to you, Ben.
Hey, thanks a lot, Marcello. And yeah, what I'm going to talk about now is some work I've been doing together with a number of our other AI scientists at SingularityNET, which is oriented toward using agent-based modeling and some AI tools to try to simulate, the spread of COVID-19 through populations, and also to try to understand what sorts of policies or interventions might be really helpful with that, with COVID-19. And yet, obviously, COVID is it's a current problem which is causing annoyances in all our lives and costing the world economy tens of trillions of dollars. And what most of us are living through. And I mean, I was in mainland China when COVID broke out. Then I was in Hong Kong, South Korea. I'm in the US at the moment. And what you see in all these jurisdictions is policies put into place that are impacting tremendously the lives of a huge number of people at great economic, social, psychological costs, based on very crude data, and in some cases just based on politics or basic intuition or rules of thumb. I mean, of course, there are very smart scientists studying the biology of COVID and coming up with vaccines and therapies and so forth. And I've been involved with that side of it a little bit. I mean, in SingularityNET, we're working with some folks doing clinical trials on multiple antivirals to help with COVID. We're sort of using machine learning to try to help figure out which combination of antivirals will work best for someone based on their gene expression, their genetic makeup. So on the biology side, there's been great science, but on the sort of policy side, where epidemiology meets economics, meets social networks and people's behaviors, you're seeing major policies put into place based on very crude sorts of reasoning. And I mean, I had worked in agent-based modeling decades ago when I was a research fellow at University of Western Australia in the 90s, and I had seen there were scientific modeling paradigms that could give more insight into things like how will COVID spread and what are the best policies for palliating and managing the spread of COVID. And it sort of baffled me that given the incredible cost to humanity, imposed not just by the virus, but by some of the policies being put in place against the virus, given this huge cost, it baffled me that there wasn't more effort going into really sophisticated modeling of COVID and its spread. So yeah, it was with this in mind that in April, my colleagues at SingularityNET and I organized the COVID-19 Simulation Summit, which was that was an event gathering together a whole bunch of researchers who were, running some simple at the time simulation models of the spread of COVID, and also introducing, theoretical and scientific concepts related to simulating COVID. So since that point in time, we've been doing a lot of different things at SingularityNET, but among that, we've put a bit of our developer and science time around the edges into advancing simulation of COVID-19. And what I'm going to tell you about today is, some of the early results that we've gotten from this work. So high level, what agent-based modeling is, it's sort of like the game SimCity that I played eons ago. I mean, instead of just setting up mathematical equations, like differential equations for the spread of COVID. You actually set up software that has a bunch of little simulated people. I mean, that doesn't mean they have to look like people and walk around like in the SimCity game, although you could make that kind of user interface. But I mean, what it means is that there's a software object for this person, a software object for that person, a software object for the other person, and those people are, you know, during the time scale of the simulation, they're going to school, they're going to work, they're going home, they're spreading virus to each other, and you studied this simulated society of simulated software people, and you see how COVID spreads among those people under various assumptions, and this can be a better approach to modeling the spread of a virus than the more simple equation-based approaches. And I mean, we're still, while we've been working on this, so in the background, just time slicing with our many other projects for a number of months now, we're still at the early stages in our agent-based modeling of COVID-19, but we have at this point come to some tentative but interesting possible conclusions. And one of the directions we've been looking at is how COVID-19 spread intersects with the structure and dynamics of the social network of people. So what we found is sort of how clumpy or how localized the pattern of interactions between people are impacts greatly the spread of COVID-19. So I mean, if you could encourage people to channel more of their interactions either with people who live near them or with people in the same tribe as them or whatever, the clumpier the interactions in the social network is, the easier COVID becomes to manage in a bunch of highly specific ways, which I'm not going to tell you about. So let me first just overview what sort of simulation model we're talking about here. So we have a bunch of different types of people. We have babies, toddlers, school kids, working age adults, and elderly people. And we haven't segmented it beyond that, but we have these 4 categories of people. And we have some people who stay home all the time, some people who go to work, except in a lockdown when they stay home, some people who go to work even during a lockdown because they can't do their work from home. Some who are factory workers, some retail workers, which have different patterns of interaction. Like factory workers only interact with other factory workers. Retail workers interact with ordinary people. Healthcare workers, essential workers, transportation workers. So we have people of all those categories buzzing around our little simulation world, and we're trying to model the spread of COVID. We're also modeling how much money they make. So I mean, if someone can't work because of a lockdown, but they're still shut at home, they're not making money, right? And then we're looking at various kinds of locations. These simulated guys can move around between like houses, apartments, offices, shops, schools, hospitals, factories, bars and such. And the people also, the simulated people also have different levels of health. Some can be immunocompromised or sickly. Some can be very healthy. So, you know, there's a fair bit of complexity to setting this up because you need to sort of quantify each of these aspects of the simulated guys moving around in the simulated world. There are some behavioral and psychological properties also. So some simulated individuals can be more risk tolerant or more risk averse than others, and some are more likely to copy those they see than others, which you can call a herding behavior. And by tweaking the personality characteristics of different agents, then you'll get different results from the spread of COVID through the population. I mean, you can go further and further with this. Like we thought of introducing polarization, where if people similar to you do something, you copy them. If people different from you or who in a different tribe do something, you specifically do the opposite of them. And you could argue we've seen that in the U.S. recently with some like mask wearing becoming a politicized thing, so that it's part of the whole political polarization. But we didn't get to polarization yet. We did model risk tolerance and herding behavior. Now, we haven't, in the last couple months, we haven't been dealing with a realistic geography, though we did some of that earlier. We decided just to try to focus on what are some general dynamic phenomena here. So we're looking at a town, which is just like a square grid with little neighborhoods, which are the little squares in the grid. And yeah, I should have a picture here, but we've been focusing on getting meaningful simulation results rather than making pictures. So we'll have a nice graphic interface for all this within a couple weeks, and then we'll release some movies of the simulations. But for now, I'm just going to tell you what the results are, which are quite interesting, even without animations of the little guys moving around. So you have a world which is a bunch of little squares, and then a school district could be a bunch of squares, like 2x2 or 3x3, and a work district, which is a simplification introduced in the model, is sort of, how far away from the office do people working in a certain office seem to live. So by making the school districts and work districts bigger in this simple simulation, you're controlling interaction patterns of the people as they travel. And this lets us get to one of the main things we've been exploring, which you can think of as clumpiness in social networks. So the degree to which a social network is partitioned into subnetworks where most interactions occur by people within the same subnetwork, right? So in the simple simulation, like the bigger a school district or a work district is, the less clumpy are the social interactions. So if most people are going to school and working close to home, then interactions tend to be clumpy. The social network is sort of partitioned by physical location. And if most people are traveling a long way to get to school or to work, the social network is less clumpy. There's more sort of even like well mixing of people. Now, clumping by physical locality where you live is not the only kind of social network clumpiness that can happen, but it's certainly a common kind and a simple kind to measure. So that's what we've been simulating now. So I'm going to show you some interesting charts and graphs from our simulations. But first, let me tell you what are some of the high-level lessons that are coming out of these charts and graphs. So basically what we found is if you have enough clumpiness, and there can be sort of a clumpiness threshold, where if the clumpiness is over a threshold, you see certain phenomena. If it's under a threshold, you see others. If the clumpiness is over the threshold, so the interaction is localized sufficiently much within social subnetworks, then doing lockdowns can be a lot more relaxed. Like it doesn't matter that much exactly when you trigger them. It doesn't matter that much how long they last. You can be fairly loose with putting lockdowns in place and still avoid overwhelming the medical system. And in a population where interactions are well mixed and it's not clumpy enough, then the particulars of when you trigger a lockdown and how long you keep it going are a lot fussier, and you may need to be more severe. And interestingly, the clumpiness also impacts herd immunity significantly. So, you'll read in the paper sometime like herd immunity is triggered when 60% or 70% of people or something have immunity to a virus. Now, under certain assumptions, that's true, but most of the calculations about herd immunity are based on an assumption of well mixing in the population, and also based on an assumption that the population is homogeneously susceptible to infection. So if you introduce heterogeneous susceptibility to infection and you introduced clumpiness of social interaction, actually the amount of the population that needs to be immune to get herd immunity can become much less. And again, there's some nonlinearity there. So if the social network is clumpier than a certain threshold, then you can start to get it can be a significantly lower percentage of population need to get herd immunity. So herd immunity depends on the nonlinear dynamics and the attractor state that the population in. It's not something you can just quantify independent of a specific population and its developmental trajectory. So these conclusions, and I'll show you some of the graphs that have led us to these tentative conclusions, but they lead to some tentative policy suggestions. Like if you can direct people to have most of their social interactions within limited size clumps, that's going to nudge the spreading dynamics of COVID-19 in a more attractively manageable direction. So if you're talking about opening schools, something I hear a lot about because my sister is an elementary school principal and they're still teaching teaching by distance learning, which is a real problem for younger children. I mean, opening an elementary school, which mainly serves students in a local area near that school, not as big a problem. If you're opening a high school university that's pulling students from all over the place, more likely to be a big problem, because it's more so breaking the clumpiness of social interactions. And you could get fancier with this, right? Like if people are going to dine out in restaurants and go to the supermarket face to face, you're going to be a lot better off if they go to the restaurants and stores near their homes. So how could you encourage them to do this? I mean, you could easy to think of mechanisms, although this is beyond the sophistication that most jurisdictions in the US are currently attempting to undertake. I mean, you could imagine like some sort of public health reward point. You get more points for ordering takeout food or getting your deliveries at home of your groceries, but you still get a bunch of reward points for going to a restaurant near your house or going to the store near your house. Then these reward points, I mean, they don't have to be liquid crypto tokens, so that would be cool. I mean, they can be like frequent flyer miles that are used to get discounts and upgrades and so forth. So you can imagine like non-oppressive, freedom and privacy preserving incentive mechanisms that will reward and incent people to clump together more socially while the pandemic is here. And these can decrease the amount of the population that needs to become immune to give herd immunity. They can decrease the number of people infected at any one point in time, which decreases load on the hospital system. So let me show you just a little bit of the simulation data that we're looking at. And I mean, there's a blog post on SingularityNET.io website, or blog.singularitynet.io. I have 2 blog posts posted just over the weekend on these simulation modeling results, and they go over sort of what we did in more detail. If you really want to geek out, there's links in the second blog post to the IPython notebooks, which run through the code and the results. It's all open source code. So what we see here at the top is a simulation with sort of well-mixed interactions and no lockdowns. At the bottom is simulation with realistic amounts of clumpiness in the social network and no lockdowns. There's zoomed out graphs, and then there's more zoomed in graphs to the right of the screen, which just show the bottom, so you can see what's happening at the bottom. The pink line at the top is economic well-being, and the gray line at the bottom that's sort of humping up and then going down, I mean, that's the amount of infection. So I mean, you see in this case with no lockdowns, with non-clumpy interactions, you see the peak infections. The gray line is going much higher, whereas with clumpy interactions, the peak is lower. Now, without lockdowns in these simulations, pretty much eventually people will get infected until you hit herd immunity, right? So there's going to be a lot of people infected. You are with a clumpy situation, you're hitting herd immunity at a lesser degree of infection. So fewer people are being infected during the whole year simulated. So this slide basically just shows how clumpiness in the social network and in our simulation model, even if there's no intervention, it slows down spread, which is not too surprising. But if you look at clumpiness, and we have a quantitative measure that's explained in the blog post, but clumpiness factor of 10 in this simulation gave us statistical properties similar to New York City and some other places in the real world. Clumpiness factor of 1 is just well-mixed interaction, no clumping in the social network. I mean, then you see, as the clumpiness gets toward the realistic level, you have a sort of nonlinear decrease in the percent of the population that has to be immune in order to get herd immunity. And that it's interesting that it's not a straight line, right? It's flat, and then it starts to go down. So it's sort of a threshold type phenomenon, which can be more extreme than this, given some other assumptions. But even in this form, it's sort of interesting when you're seeing going down from like 80% to 63% or something immunity needed to get to herd immunity. Now, if we look at a clumpy situation with lockdowns, I mean, what we see is that, you know, the lockdown works. So here we're triggering the lockdown when there's an infection rate of 0.4% active cases in the population. We're listing it when we've been lifting lockdown when we've been under that level for 7 days. And so, you know, the one lockdown works. You see the gray line goes over the critical threshold, but then the lockdown's in place. It goes back under. Lockdown's lifted, and then once it's lifted, the pink line, giving the economic health, starts going up again. The economy starts bouncing back. Now, what's interesting when you do a stricter lockdown in this clumpy social network, very strict lockdown when there's 0.1% of the population infected, you know, the story's kind of the same in terms of infection, but here with our assumptions, the lockdown never stops because we're assuming it's like a small town and there's some folks with COVID just migrating in now and then, which keeps you at 0.1% infected. So even though here economic activity is like flatlined, you're not that much better off in terms of the infections, because the clumpiness keeps things down anyway. So when you're in a clumpy situation, like in the top here, you know, you're a little worse off with a lax lockdown than a very strict endless lockdown, but not that much worse off, which is interesting. The clumpiness means you can be a bit laxer with a lockdown. Whereas if you're in a scenario with no clumping, like well-mixed social interactions, right, then we can see here, like the top is locked down with a 0.4% trigger. The bottom is locked down with a 0.3% trigger, not even 0.1, like not that different, but you're seeing a fairly significant difference. I mean, if you look at the gray curve on the zoomed in graphs, I mean, you can see the infections are going down significantly more with the 0.3% at the bottom than with the 0.4% at the top. So there's a measurable difference in the consequences of the amount of infected population based on a quite small difference in the policy trigger for lockdowns. So that, I mean, and that's what you see. That's what you see when the clumpiness is below the clumpiness threshold. And you know, I don't expect you to scrutinize these data tables here, but if you look at the blog post on SingularityNET.io, it goes through it. But what you find in general is when you have low clumpiness, then yeah, herd immunity is harder to achieve. There's a higher threshold for it. Peak infections are higher, but also the differential amount of value you get from a stricter lockdown is greater. And when you have clumpier social interactions, for example, caused by more interactions being especially localized near a person's home, when you have clumpier social interactions, I mean, yeah, it's easier to get herd immunity with lower percent of the population immune, fewer people are going to be infected, but also you can get almost the same effect with a fairly lax lockdown policy as with a strict one, which is pretty interesting. So I mean, we're definitely still at the early stage in our simulation modeling adventure. This has sort of been a background project because at SingularityNet, you know, we're building a decentralized AI platform. We're incubating the Singularity DAO. We're doing a bunch of different sorts of AI research, being AI networks on the platform. It's not like we're a COVID simulation modeling agency, but I think we've gotten far enough now in our work on this that we can see there's a real lot of promise. Like I mean, working with these very simple models is interesting and valuable because it shows you sort of what are the generic and archetypal phenomena, right? But still, you do want to build in-depth models of specific cities, towns, and countries, even integrating data from all over the place. And you know, publicly available data that we have now will let us go a long way, but how much better it would be if we had more data, right? So we're going to have a talk later in this D.OS event, I think, by Dr. Deborah Duong, who's been my colleague since I don't know, 2002 or 3 or something. And, you know, we worked together on agent-based simulation in DC way back when. So Debbie did a lot of the simulation models I'm describing to you here. And she's also done a bunch of the AI behind the Rejuve COVID app we've been working on, which will be launched soon, which that lets you monitor from, from digital thermometers from your Apple Watch and so forth, and then report your biosignals, which can help tell you early stage, like pre-symptomatically, if you might have COVID. But also, I mean, if you, in a secure, privacy-respecting way, as we can do with our SingularityNET blockchain-based network, if you take data gathered from multiple people using such apps, this gives you quite interesting data to feed into agent-based models. You can get more and more accurate. So I mean, what we're doing here with simulation modeling, I think, has shown great promise already, and we're going to be writing up formal research papers on this, as well as have some meetings lined up with relevant policymakers. But this is just part of an overall pipeline. I mean, we need to collect more data, aggregate and analyzing it with machine learning algorithms. We need to make more detailed agent-based simulations. And then, the policies that are designed based on these simulations, the impact of those policies can be tested in simulations. Then we need these policies to be deployed. And I mean, I saw exciting news today that the Pfizer's COVID-19 vaccine may be up to like 90% effective, although we didn't see how effective it is for the elderly or immunocompromised who are at the most risk from COVID-19. But I'm a big fan of biological science, and I do think we're going to get a vaccine before too long. I mean, I think there's still going to be a significant period when managing COVID intelligently with policy is going to be relevant before a vaccine is widely rolled out. So I think agent-based modeling is going to be critical for getting us through, say, the next 6 months or whatever it is before a vaccine is widely rolled out with more intelligent and nuanced policies. We should be using these sorts of models and other sophisticated modeling techniques now to determine when to open schools and when to open restaurants, to make incentive systems. So I think even though we're getting toward a vaccine, we've still got many trillions of dollars of economy that's being screwed up by very simplistic policies that are determined by intuition and politics rather than science. We need to be rolling out agent-based modeling, all over the place to determine policies more intelligently. The cost to fund a bunch of modeling activity is really trivial compared to the economic, psychological, and social cost of the policies that are in place. But I also want to, as I wrap up, look beyond COVID-19. Like I know, I've been around 53 years on this planet in this incarnation at any rate, and I've seen a lot of humanity. I'm pretty sure that once we get the vaccine and COVID-19 is beat, almost everyone's going to be like, all right, that shit's done, let's party, right? I mean, there's not going to be a lot of pandemic awareness once the vaccine is released. But I could also tell you, this is not likely to be the last nor the worst pandemic that humanity faces, before we get nanobots that can go into our bodies and cure any disease or mind upload or whatever it is, right? I mean, we could view COVID-19 as sort of a dress rehearsal for the worst pandemics that are probably going to come, and we don't know when. It could be 5 or 10 or 12 years. So we certainly want to be sure that when the next and possibly worse pandemic comes, we're a hell of a lot better prepared than we are right now. And I mean, that will involve, secure, privacy-preserving tracking apps like the Rejuve app. It should involve scalable machinery for secure and privacy-preserving agent-based models. So when something else hits again, you just click go, right? And I'm also viewing this, just to briefly hark back to Charles Hoskinson's, brilliant initial keynote here. I've written before about what I called Robama. This was obviously in a few years ago, before we had President Trump. I'd written about the notion of Robama, like an AI-based government decision support system, which was going to just help human leaders make decisions about every aspect of society. I very much believe we're gonna need that. I mean, we're humans. We want human leaders for value judgment and for what they can do in terms of reaching out to their constituents and educating and building consensus. But the complex decision making involved with the modern society, we're going to be better off with an AGI system to do that. So I think pandemic response and agent-based modeling, as well as incredibly important on its own, it's also sort of a testing ground and playground for ideas for automated governance decision support, which can later be rolled out in a whole bunch of other areas of government also.